Welcome to the 10th video of the series of Introduction to Quantum Mechanics. So far we have been talking about the dual nature of light, that is light made up of particles or is it a wave? As we saw in the second video of the series, this debate dates back to the 17th century. It took more than 200 years for the researchers to conclude that light is made up of particles as well as it's a wave. It has dual nature, or on a lighter note you can say that it suffers from a split personality disorder. But as far as electrons are concerned, there was no such confusion. They had a definite mass, charge, they were deflected by electric and magnetic fields, and they even left a sharp mark on the screen as cathode rays. They were thought to be tiny particles that created no problem, unlike the particles of light. But as it turns out, they were not so innocent. So in today's video, we are going to talk about the mischievous nature of electrons and the experiment that exposed it. So before we start, make sure you subscribe to this channel and press the bell icon so that you don't miss any future videos of this series. Electrons were first discovered back in 1897 by J.J. Thomson. Like I said before, there was no confusion related to electrons. They were considered to be particles. However, in the year 1923, de Broglie, who was just in his 20s, suggested that even electrons have a dual nature. That is, just like a wave is associated with the particles of light, in a similar manner, a wave is associated with the material particles such as the electrons. De Broglie even calculated the wavelength of these matter waves. That wavelength was lambda is equal to h upon p, where h is the Planck's constant and p is the momentum of the particle. Now how do we derive this? It's very easy. Consider the particles of light. For them, the energy by Planck's law is given by h nu, where h is the Planck's constant and nu is the frequency of light. On the other hand, Albert Einstein gave his own relation of the energy, E is equal to P into C. We discussed it in the video of the Compton effect, the 8th video, where P is the momentum and C is the speed of light. When you club these two equations, that is, when you equate the right hand sides of these equations, you get h nu is equal to P into C. And now you have to change frequency in terms of wavelength, that is h. Nu is c over lambda. This is the relation between the frequency and the wavelength is equal to p into c. Speed of light gets cancelled on both sides, so you are left with lambda. This goes here and this comes down is equal to h upon p. This is how you define the wavelength. De Broglie generalized this relation to every particle having non-zero mass. But de Broglie did not have any experimental evidence to support his hypothesis. The experimental verification of de Broglie hypothesis came 4 years later when two scientists accidentally found something they were not even looking for. In 1927, two scientists, Davisson and Germer, were trying to understand the angular distribution of the electrons when they are scattered off a nickel foil. Now remember, they were not trying to prove the de Broglie hypothesis, they were just doing their own research. But then something amazing happened. Due to some reason, air got leaked into the evacuated chamber that contained the nickel foil, and because of that, the nickel foil got oxidized. Now in order to expel the oxygen, they gave the foil a heat treatment and resumed the experiment. Now when the two scientists performed the experiment, they were shocked to see the result. Of all the possible scattering angles, now there was just a single angle at which most of the electrons were being scattered, and that angle was a function of the initial kinetic energy of the electrons. So suppose the initial kinetic energy of the electrons is 54 electron volts, then most of the electrons were scattered at 50 degrees. Graphically, you can represent it as a curve between intensity of the electrons and the scattering angle. So you can see that at 50 degrees, for a 54 electron volt electron beam, The peak of intensity is at 50 degrees. That is, most of the electrons are being scattered at an angle of 50 degrees. Now this graph was familiar to them. They had seen it before. This variation of intensity with the scattering angle is the same graph that we see in X-ray diffraction. So they immediately knew that they are directly looking at the wave aspects of electrons, because they weren't using X-rays in their experiment, they were using electrons. Hence they knew that they are now looking at the wave aspects of electrons or the matter particles. But what exactly happened after we treated the nickel foil with heat? What's changed the experiment? The answer is the foil got well crystallized. So the atoms of the foil were well arranged in regular patterns. A part of the waves got diffracted from one point, a part from another point, and so on. This created a path difference, and hence we observe a diffraction pattern, which is a wave phenomena. Davisson-Germer experiment confirmed the de Broglie hypothesis. So now we know that with every matter particle there is a wave associated with it. Smaller the particle, more prominent the wave nature becomes. Now if this is true, it must be possible to perform Young's double slit experiment with electrons also. When you do that, electrons do show an interference pattern on the screen thanks to its wave nature. Even if you use a weak source such that the electron goes through the slits one by one, wave interference takes place because the waves associated with the electrons pass through both the slits. This concludes the 10th video of this series. In the first 10 videos, we have learned how quantum mechanics was born. We started with what is quantum mechanics and how is it different from classical and statistical mechanics. Then we went back to a 17th century debate between Newton and Huygens on the nature of light. Then we discussed the Young's double slit experiment, black body radiation, Planck's law and its applications, the photoelectric effect, the Compton effect and its applications in astrophysics, and finally pair production and de Broglie hypothesis. The reason behind the introduction of these concepts was to show what exactly went wrong with classical physics and why we had to invent new physics. From the next video onwards, we are going to learn the core concepts of quantum mechanics. We'll be starting with the wave function, which is one of the most important parameters of quantum physics. So see you in the 11th video of this series. And before you go, make sure you like this video and subscribe to this channel. Thank you.